Moving on to section 1.4 in Stewart. Here we're going to talk about exponentiation. So we understand exponentiation as an operation, but we're going to broaden that to thinking about it as a function of real numbers. And in order to get there, we should think about what exactly it is. So our basic definition comes from historically thinking about exponentiation in terms of whole number powers. So we begin with some real number, a, that we're going to assume is positive. And n is going to be a natural number. In other words, when we think about a raised to the n power, we think of a as the base and n being the exponent. And the act of taking this new real number is exponentiation, where we're multiplying a by itself n times. So if you're following along in terms of what this looks like for actual numbers, let's think about the powers of 2. So powers of 2. We have 2 raised to the 1, 2 raised to the 2 power, 2 raised to the 3rd power, and so on. So the first one is obviously just 2 once. Second one is 2 twice. Then 2 3 times. Oops. And every time we get larger and larger numbers. Recursively, we can also think about it as 2 to the n is the previous one times 2. We just keep multiplying 2 and keep nesting this idea of adding another, not adding literally, but multiplying by another base. So this is where we start. But we can broaden this further to integers, integer powers. Well, we now introduce things like zero exponents. So the zero exponent rule that says any number raised to the 0 power is equal to 1. There's a caveat here where we say except for a equals 0, but then we make a stylistic and actually logically valid choice later on to just call 0 raised to the 0 power equal to 1. Okay. And once we introduce integer powers, now we can think about negative exponents. So something like a raised to the negative n, where n is a whole number, is going to be the same thing as 1 over a to the n. Again, provided a is not actually equal to 0. So in practice, this means something like 4 raised to the negative 2 power means 1 over 4 squared, which is actually 1/16. So you'll notice now that if we think about exponentiation, we now get this clear idea that if you take higher natural number powers, you get larger numbers. So your a to the n gets larger and without bound. On the other hand, if you plug in more and more negative exponents, so for instance, 4 to the negative 3 would be 1 over 4 cubed, which is 1 over 64. As you go down here, your a to the negative n's get much smaller. Okay? But we can go one step further and say, what if we take rational numbers as our powers? So rational powers. Now we're talking about things like a raised to the m over n power, which is the same thing as nth root of a to the m power, or nth root of a raised to the m power. And this works every time, as long as m over n is a valid rational number. And this introduces even more to the exponentiation operation. It's at this point, actually earlier, that we discuss and rely on what we call the exponent rules. So we've already discussed a few of them, but we also have things such as the addition rule, which says that if you add two powers, then it's the same as raising the base to the n power times raising the base to the m power. You also have things like the subtraction rule, which states something like, if you subtract one power from the other, it's the same as taking a to the n divided by a to the m. So, yeah, this is usually called, okay, I think it's usually called the product rule. And this is the quotient rule for exponents. Okay, make sure you're clear that this is just for exponents. And then you have things like a to the n raised to the negative 1 power is the same thing as a to the negative n. And things like the power rule, which states that a raised to the n power raised to the m power is a raised to the n times m power. And that's the power rule. Okay. Now, all this is to say that if we're trying to think about this as a function on real numbers, up until this point, so far, if we define f of x equal to a raised to the x power for x being any rational number, and if you fill in the graph for something like, for example, f of x equals 2 to the x power, and it could be any base that's greater than 0, right? So it could be 1/2 even. Then you end up with picture. So if we take a small table of values, for instance, we'll take -3, -2, -1, 0, 1, 2. We know that 0 gives us 1. 1 gives us 2, because that's 2 raised to the 1 power. 2 raised to the 2 power is 4. Then we have 1/2 on this side, 1/4, 1/8. All right, so if we plug in these values, so -3 and 1/8, very close to the x-axis, almost negligible. -2 there, -1 there. Plug in 0, you got 1. Plug in 1, you get 2. Plug in 2, you get 4. And so on. 3 gives you 8. Okay, so there's a clear trend here that you can fill in with the rational powers of 2. And it's this infinitely dense line here that's also full of holes everywhere. But the beautiful thing is that we can extend this definition so that f of x raised of a to the raised to the x power, so long as a is greater than 0, is the exponential function base a defined for all real numbers, literally all real numbers. And that's done by filling in the gaps there in a rigorous mathematical way that's beyond the scope of this course. So our consequence is that arbitrary powers of positive real numbers are well defined, and in the coming video, we're going to discuss how to graph these functions.